Alright, I wonder if we're streaming. Alright, before I forget, let's... Alright, I think we're streaming. First off, we need to simulate a handful of basic designs. Because it is important to understand these designs from a very basic concept standpoint. Now let's see. We also need to do this in 3 dimensions. Before we go any further, I have to do this in 3 dimensions. So, actually, first, let's do this because this will give us a better context of flow paths. That's what this is all about. Actually, if anything, this should be the other way around. Because that is going to bother me. This because, again, this is going to bother me. Just to give a detailed explanation of what the hell's happening. Alright, and then we do this in 3 dimensions. Alright, so now that we have that set up, oh, before I forget, because this is also going to be important. First start out with a simple line. This will be our introduction to Fluid Dynamics 101 and how it relates to power production . Alright, first things first. We need to understand what we're looking at. Now that the class is all set up and ready, let's begin. We will come back to these here shortly. These are basic principles of intakes. Now, this line here with the blue, the green, and the black, this is the simplest principle of a water hammer, or rather a fluid hammer. And we are defining fluid here as a liquid or a gas. Anything that can flow through any kind of conveyor tube, vessel, whatever it be. It is a item that is designed to flow, and all it does is flow. Following along so far? Good. Now, to give a better explanation of what's happening here, our fluid, which for sake of argument is going to be water here, or air. We're going to use air a lot because in explaining what an engine is, these over here, these are as close of a representation of an engine as I can make. So, bear along. Our fluid is air in this diagram here, and is moving in this direction. Now, according to Isaac Newton's laws and principles of matter, mass, and related subjects, an object in motion tends to stay in motion unless acted upon by another force. This is simple science. This is true with fluids, whether it be air, or any kind of gas, or any kind of liquid. Now, a fluid hammer is what happens when you have a sudden increase in pressure. What that means is that our fluid is traveling down the pipeline, as it is here. This black block right here is a valve that suddenly shuts. This green block right here is the sudden spike in high pressure, because all objects in motion have inertia. What is inertia? It is the tendency to not stop moving when in motion. So the second that door shuts, you have a sudden spike of high pressure that ripples backwards, going up the pipeline. This can be noted by a noise when you turn off the faucet at an incredibly high speed, say in an old house. That you might hear is the pipe shaking because of the same principle. Now, the reason we are discussing this before even getting to any of this is a basic principle that all engines use in terms of power production, and it is how all engines operate. All an internal combustion engine is, whether gas or diesel, is a giant air pump. That is all it is, bar none. And how it is powered is controlled detonations, explosions of a fuel substance, whether through compression ignition or spark ignition. Now, moving along from there, why you want some of this to happen in a normal engine for reasons which we will get back to shortly. Now, we're going to be discussing hemis here shortly, and by principle of association, their relation to overhead cam engines and why those type of engines typically make good power. But to understand that, we first need to understand power production. Now, this first three-dimensional sculpture that I have drawn here is that of a representation of a flathead Ford V8. Now, why does this matter? Well, simple. Actually, most Fords have a much shallower. In fact, not even. We usually have that kind of deal. Bear with me, it's artistic licensing here. Now, the yellow and orange and light blue is our air-fuel mix inside the combustion chamber. The red is the exhaust gas going through the tubes. The Light blue concrete is our air-fuel mix before the cylinder. That is true of all of these. Follow along so far? Good. Alright, moving along from there. In a flathead Ford, you have what is known as a flathead engine. What is a flathead engine? Well, it's also sometimes called valve and block setup. In fact, I think I have a model, yes, right over here. Now, in simplest terms, with relation to a flathead engine, you have an intake port and an exhaust port. This is clearly a two-cylinder configuration, but needless to say, the reason we bring this up is to demonstrate how inefficient these motors are. Because the valves are inside the block, that means the runners have to be too. Thus, our three-dimensional diagram over here. As a result, they tend to not last very long. While being relatively tough for the time, a flathead Ford is getting old and tired at about 100,000 miles. That is about the limit of the motor, to give context. And to give further context, most motors 1983 and forward it's not unreasonable to ask 200,000 or even 300,000 if you take care and don't beat the shit out of a motor from that era and moving forward. So, perfect example. It is not unreasonable to expect, if you're being gentle on it, to get an LS motor, say an LS1, just a 350 LS, to ask 400,000 miles out of its lifespan. It is not unreasonable because the technology has gotten better, parts have gotten better, and if you are nice and gentle, quote unquote, with it, then it could potentially last that long because, well, designs have gotten better, things are not as sloppy as they used to be, etc., 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 etc. Improvements in technology, etc., etc., etc. But how does that relate to power production? Well, moving forward, in the early days, all we had were flathead engines, and as a principle, their power production was at best limited. With the best Ford V8 with the whole hot rodding book thrown at it, all it could make at best was 190, maybe 200 if you're hot shit, maybe 230 with a supercharger. That is the hottest hot shit motor. That is, oh my god, you're gonna be fucking killing yourself with that screaming metal death trap fast. That was what was considered fast. That is all that motor is capable of, relatively speaking. Now, I'm sure there are guys out there that could probably get 300 out of them, but, well, the reason they can only get that much out of them is because of this runner design. Because the runners, the tubes that feed into and out of the cylinder, are limited in their scope, it means that you can't really port and polish them, and this is the reason why. When it comes to hot rodding, the smoother your airflow, the more, in theory, flow you can do, because there's less resistance to flowing because of a smoother surface, because there's less drag. It's simple aerodynamics, simple fluid dynamics. A smoother surface tends to be slipperier through the air. And as a result, because of their weird runner design, as I've demonstrated here, if this is our combustion chamber, this is the runner in, and this is the runner out, there's only so much you're going to be able to do with a polishing tool. And even then, you're going to end up backing up against a restriction. So therefore, you are never able to really make any kind of good horsepower out of these motors. Then overhead valve configurations started coming around. This type of flow path is what we know as a reverse flow cylinder head. That means it goes in one way and out the same way. like so. Which, because it's an overhead valve engine, means that, in theory anyways, you're able to potentially make more horsepower by a little bit. But this also, while you're able to, because the ports are straight in and out, because the airflow has to make 180 degree turn going into and out of the cylinder, it means that you have a lot more restriction. Not necessarily because you have a ported cylinder head. A ported polished cylinder head will still make more power, but because of the nature of the way the flow is allowed to go, it means that the air has to stop, sit, settle, and then start again, which means the motor works harder and therefore is less efficient. This type of cylinder head design is very, very prevalent in inline 6 and inline 8 engine configurations, and they did this not because of this design here, which we'll get to in a second, not because they were looking for power, but because they were looking to be able to start every time. Why does this matter? Well, here's why. Carburetors. For a very long time, most engines had their fuel delivery system done by a carburetor, which ironically actually is better for power production, as Engine Masters has found out. And that has to do with a whole bunch of science related to inlet temperatures and the like, but we'll get to that another time. That's another video in it by itself. God, we've already been talking for 15 minutes. Shit. No, the reason they did this is to keep the carburetor warm in cold temperatures. That way it would start easier. Because if you didn't, you would have an engine that would just drain your battery until it finally kicked over, and which means you'd have to have it sit. The problem with that is that it's a double-edged sword, because in hot temperatures you'd have the reverse problem. Because the engine's getting so hot, you would actually have it quit out in hot temperatures because of something called vapor locking. What is vapor locking? Vapor locking is when the fuel is literally boiling inside the float bowl of the carburetor. And what that means is that, well, to demonstrate better, what you would have is a heat chamber that would come off the exhaust manifold. If I do a quick demonstration of, nope. You would have a little heat chamber that would sit right here. And by contrast, you would have a little absorption chamber on the underside of the intake manifold. Because they bolted up the same, in fact, if you do this, I'm just trying to exemplify what I'm talking about here. So, uno momento, if you please. No, I'm not kidding. This is literally how most inline 6 engines were done. You would have a heat transfer chamber that would, if your general manifold outlet was right about there, it would sit right about here. This little resonant chamber would transfer heat up to our carburetor right about here, which would usually be a 1 or 2 barrel carb of some description. This was usually done on base model motors. And the reason you don't want this is because in hot temperatures it would vapor lock, because this would be getting so hot that the fuel at, say, 70 degrees Fahrenheit would bump up to the boiling point of gasoline, which would mean that you're not getting enough fuel, and you would have to sit an hour for the engine to cool down to kick it over again, because otherwise you're just going to drain the battery. And they did this because in cold climates you have, again, the reverse problem, where you would want this to be warm because cold fuel at a certain point doesn't work, period, dot, the end. So, as a result, reverse flow cylinder heads, as exemplified here, just don't work. They don't like to make power. because making that 180-degree turn back out basically the same way it came in doesn't work well for them. So, with a lot of V8 and V6 engines, and even some V4s and some later inline style engines, they started making cross-flow cylinder heads, which were, for their time, a revolutionary upgrade. Now this allowed for more traditional flow patterns, which we see all the time today. Now, this is a typical V8 style configuration, say LS, Windsor block, small block Chrysler style valve arrangement. You have your intake valve here, your exhaust valve here, and that's the flow path the air has to make. This, by virtue of its design, is better. So much better, because it allows the air to, while slowed down, still continue moving in the direction it wants to move. And depending on the cylinder head's combustion chamber design, can even be amplified, because to use a reference, the 302 cylinder head in small block Chryslers, 318s and 360s from the late 80s, early 90s. Let's see, this. Will want to do something like this, but we're talking about this in three-dimensional space, so bear that in mind. So, yeah, do this. Now, what I'm trying to exemplify here is the way the flow path wants to work. What you have is your air charge coming in like so. Wait, I needed that one. Coming down, and because of the way the combustion chamber is shaped, the valves help stir the air. Now it'll still want to make that 180-degree turn, but because the airflow path allows it to move that way, it also means that in this motion, in fact, we kind of point in which the direction is going, it'll start in a clockwise direction and then go up, which allows it for a better swirl pattern. That's why the 302 cylinder head is sometimes called swirl ports, which allow for better airflow, because it helps keep the inertia moving, because while it's changing direction, it's still keeping the direction that it wants to move, because it is a fluid. Now, this is what most pushrod style two-valve engines are like, and for the most part, this is something that designers of engines have to take into consideration a lot. Are we talking a performance engine, or are we talking a Joe Schmo engine? Then came the Hemi. This was most small blocks with regular... I'm not picking that up. Well, this is annoying. Anyways, where was I saying? Right, Hemis. Hemis, on the other hand, are the pinnacle of a performance engine, and by association, therefore, also overhead cam motors, because they share the same principle, which is opposed valves. What does that mean? Well, if you were to look at a cylinder head's configuration, you'd have your let's see. This is just using the LS as an example because the LS is the most common one that everyone can associate with. Let's see. 1, 2, 3, 4. You have intake, exhaust, intake, exhaust, intake, exhaust, intake, exhaust. But for example, on the, let's go 350 Chevy. This is going down the length of the engine like this, following the axis of the crankshaft, like so. So, intake, exhaust, exhaust, intake, intake, no, I got that backwards. Let's see, exhaust, intake, intake, exhaust, exhaust, intake, intake, exhaust. Same number of blocks, different, or same number of valves, different orientation. Now what this meant is that you have to take into that account of the intake design. Case in point, you see why the intake runners on these two flow paths are the way they are, and I'll explain those in a bit. This is your traditional small block valve arrangement. This is small block Ford and LS style motors and the like, which are a little bit more efficient, just a little bit. And it has a lot to do with header design and valve design. It also is a little bit easier to produce, but kind of not really. It really depends. This is more the nuanced design. This is more of the brand favoritism difference right here, is what kind of engine do you like, but we're not going to be talking about that just yet. Hemis, on the other hand, have a significantly wider cylinder head. While they may take up the same amount of space, the valves are 180 degrees opposite of each other instead of in line with each other. Why is this better? This is why. Our flow path is a straight line near enough about. How straight we talking? Well, straight enough to ping the straight, or to stand out like a sore thumb, like a straight dude at a gay bar. That's how straight. Well, I don't think that expression works, but you get what I mean. Because it has the valves, well, actually, it's more like, I should be more appropriate with my design. It's technically more like this, but you get the point. Because it's virtually a straight line, although with a slight bend in it because of the combustion chamber and the cylinder head that has to go down and then back up, it is virtually the best performance design with opposed valves like this. This is why a lot of overhead cam motors are set up in the same fashion, albeit not necessarily with a hemispherical combustion chamber, usually, but with a similar enough design that with either Quelch pads, which is what this style of combustion chamber is actually called, which helps flow being good, usually a double Quelch pad because that allows for 4 valves per cylinder. But again, jumping the gun here, what this allows is a more consistent flow and helps draw better vacuum. Why does vacuum matter? Why are we talking about vacuum? Well, we're also talking about positive and negative pressure sides. Depending on the setup, if we're talking naturally aspirated, we have a negative pressure side going into the cylinder head and a positive pressure side going out of the cylinder head. This is one of the reasons why exhaust gases are so hot. It's partially because mostly because of the spent fuel, but also partially because it's being pressurized. And we could talk into header length and design and all of that, And if you were to spend the time and the money to calculate it all out, you could have one massive header, single header for a V8 that would be purposely designed to be magnify the exhaust pulses to help scavenging, which again, not really the subject of discussion at present. We'll get to that in a moment. But needless to say, it can be done. But the reason you want this is because of this linear line. Because there's less restriction to flow. Because of that, it just performs better. Now, albeit, I'll make note, hemis, naturally aspirated anyways, don't really come alive until about 5,000 RPM. That's when you're really pulling enough vacuum through the intake manifold into the cylinder head that you're getting that fluid hammer effect. What am I talking about again? Right, this. Because all an intake valve is, or exhaust valve is a door. Now, here's something else to keep in mind. This works in reverse. Now, what I didn't show was the other side, the side that had the flow cut off from. Flow pressure doesn't start picking up until way later because you're drawing a vacuum right here. Because of the pressure pulse, because of the lack of fluids, air especially, is very, very stretchy and very compressible. Think of it like a rubber band. When you slam that door shut, you have a negative pressure void. This is called cavitation. And that creates a near vacuum behind the exhaust valve, which actually kind of helps it keep it closed, but not really. It's minutia we're talking about here. And this is what we're talking about when we're talking about exhaust pulses. And we'll get to that in a little bit. Now, this matters, this entire big stretch of vacuum matters because it helps pull air out of the cylinder. Because once that valve opens again, the exhaust valve, it's not just the piston pushing out, it's also the vacuum pulling it out. That's why I'm saying it's called a positive pressure. Well, that's why I'm saying it's a positive pressure on the exhaust side up until the valve closes. Once that valve closes, all that inertia wants to keep the fluid moving. But because there's no supply for the demand, you get a vacuum. And that's why an exhaust pulse happens. The same principle happens on the other side, except inverted. Follow along so far? Kinda, sorta? Good. I'm trying to keep this as simple as possible. Now, what else am I forgetting? What else am I forgetting? Shit. I can't remember now. Now, all of this being said, this is something to consider when buying a motor or buying a vehicle. Most modern cars, at least non-USDM made cars, are overhead cam motors. And a lot of V6 engines are overhead cam motors. A lot of inline fours, almost all inline fours, are overhead cam of some description. And I'm not going to hate on overhead cam motors. I may not personally like them because of, well, mile-long timing chain, personally speaking, not something I like, but I can respect the power that they put out. For instance, one of my favorite JDM style motors is the RB26. You can't argue with results like that. You really can't. Which is a double overhead cam inline 6 motor, which has the valves in an interposed arrangement, and it can be turbo or can be naturally aspirated, but that's minutia. Now, let's get back to exhaust pulses now that we have gotten the basics out of the way. Now, let's see. I'm going to set up let's set up our standard exhaust for small block Chrysler, small block Chevy, like so. actually, you guys need to be one farther apart. Let's do this. And then we do this. This is the simplest arrangement I can come up with. Now you kind of get a gist of where the flow path is. Well, actually, let's do this. This makes a little bit more sense. Now that we understand cross-flow, basic cross-flow cylinder heads, this is the simplest valve arrangement. Now, depending on your firing order really depends on your intake, or how you get your performance out of your intake and your exhaust. Now, if you're looking for high top-end RPM horsepower, you might want to consider a single plane. And we'll get into headers in a bit. A single plane implies that for each tube inside the intake, you have a port that goes directly to it. This is the simplest design, and while some folks in the past would have tried to call something like a Torker 2 or something like that, spelled but what we're getting at here is that this is really good for high RPM. This is a very racy-esque style intake, which is, like I said, good for high RPM because it flows really well at high RPM. But if you're looking for down low, daily drivable torque, actual torque, what you want is what is known as a dual plane intake. Now, what's a dual plane? Well, as you can see, the colors show the flow paths, or rather the flow tubes, the runners. What you have is a stepped flow path that is split into 4 quadrants. Well, 2 actually. Usually with most dual plane intakes, you'll have a side that comes up lower than the other and a side that comes up higher than the other. Now this balances out the intake pulses a little bit, and this is why low down torque happens, is because of those pulses, because it's trying to make the best examples up. Because let's see, if this is, well, let's call this the front right here. If that's the front of our motor, small block Chrysler firing order, 1, 2, or well, cylinder counting, I should say, 1, 2, 3, 4, 5, 6, 7, 8. Cylinder number 1 is going to be paired with cylinder number 3, because when cylinder number 1's pulse is done, cylinder number 3, or, well, yeah, cylinder number 3 is going to be opening up, which is this one right here. So it'll be pulling vacuum over here because this side is not going to have it. Cylinder number 4 is also going to be drawing vacuum about the same time that cylinder number 1 is drawing vacuum, because within a reasonably short approximation of the valves are opening a little bit closely together. Same with 2 and 3. And the same is true on the other side as well, needless to say. It is trying to maximize the torque. These are good up to about, this style, dual plane intake, are usually good up to about 4,500, about the first, I'm not going to say 2/3, but a little bit more than the first half of your RPM range on a normal V8, just to use as an example. Which is fine. That's where most of your down low torque. It's going to be good up to just a little bit past your torque peak number. That's where it likes to build power. Single planes, on the other hand, they really don't like to make torque because they're not maximized for those intake pulses. Follow along so far? Again, we're talking vacuum and high pressure situations like here. With respect to single planes, what they like to do is draw as much vacuum as a whole as possible. And that's why they excel at making high-end horsepower past, say, 5,000 in that last third. And if you have a motor that will spin that fast quickly, I would recommend this. But again, that's high horsepower applications. Well, relatively speaking, high horsepower in the sense of high RPM horsepower. Not high horsepower as in like 1,600 horse. Though, to be fair, I have heard that you can get dual planes on those as well, but we're not talking about that right now. Next, let's talk about exhaust pulses. Now, based on the header design, a lot of OEM manufacturer stuff might have what is known as a log style manifold. These aren't all that great. These are usually terrible, and they literally, I am not making this up, usually look like this. Where you'll have like a single outlet there, or there, per se. Sometimes they might get a little clever and do something like this. Which helps, kind of. There's a lot of constraints that determine OEM manifold stuff. And usually, if you're talking your classical small blocks, Windsor, Cleveland, 350 Chevy, or well, small block Chevy architecture, like 250 to 400 esque to, and LA small block Chrysler, and even the Mags, which share a lot of parts with that came after them. Usually the best OEM stuff for manifolds anyway came in design-wise anyways, not necessarily in terms of actual good power production, came from like 86, 87 to whenever production ended for that family of motors. Now, this is just one example. This is OEM examples. Now, I've seen what is known as the a header that looks sort of like this. That's nicknamed the like the gasser style header. Those can work, but usually they'll have like ports shifted like this so that it'll operate better, like so. It'll usually just kind of do one of these, and it'll have one central tube that'll get longer and longer, or larger in diameter, internal diameter, as it goes down to accommodate the addition of more cylinders. This works, but again, pick your poison. Now, depending on the situation, I have some little shorty. With regards to header design, something you have to consider: how big is each individual tube coming out of the cylinder head's diameter, how big is the collector's diameter, and how long or short each runner out of the from the flange to the main collector is, and you might even consider collector length. Now, for this, we're going to demonstrate this. Let's see, let's call this the collector, and this the runner, quote-unquote, length. Now, depending on how long and how large in diameter, ID, inner diameter, the collectors are into our header is, really makes a difference. And we need to pay respect to that with regards to how it's done and set up. Now, for example, I am building a 318, hopefully, with some cheapy $200 pair of headers off of Summit. They're 1.5 inch diameter to 2 inch or 1.5 to 2 inch collector headers. That means that the diameter ID of each runner going into the collector is 1.5 inches in ID diameter, inner diameter, and that the collector itself is 2 inches in diameter. This is kind of small. Kind of. The collector itself is only 2 inches diameter, and it's actually really short, which is something I'm not thrilled about. To give you an example, a really good setup, like really good tubular headers, will have a collector that's super long to accommodate the pulses. Let's just kind of do something like this, where you have merging paths sort of like this. Bear in mind, I'm doing a very rough job in demonstrating this, but I hope the concept is well understood. Because depending on the situation, you want it to do something like this, where it merges very gradually over a long period of time. Because that way you're able to maximize the exhaust pulses. That's why tubular headers that are really high-end stuff are usually custom manufactured. They're designed to get around shit, which is, again, something that OEM manufacturers also have to consider when building the manifolds, because you have to have clearance for the steering shaft to go to the steering box, you have to have clearance for the power steering pump, you have to have clearance for the upper control arm and shock support mount and the fender well and stuff like that. So usually they're small like this just to accommodate that. But getting back to the collector design, usually it's pretty basic on OEM stuff. That's not to say that the LS motor is a bad motor, absolutely not. It is actually doing pretty good in terms of its collector or exhaust manifold design. It doesn't suck, is what I'm saying. But headers help direct the flow path, and depending on the length and how they're set up, depending on who goes where and how long each one is, can really affect your power figures. The headers I got, they're small. I'm being honest with you there. And that isn't necessarily a bad thing, depending on what you're shooting for. For example, because they're small, it means that they're not going to flow a lot of air. Admittedly, they are going to flow better than the OEM stuff I had, but they are not going to flow as good as something with, say, 1 5/8 or 1 7/8 inch runners into, say, a 2.5 inch collector. And because the collector itself on mine is so short, like that short, it means it doesn't have a good merge because it's forced together. Usually with shitty little shorties like what I got, it'll just be one big tube that's bent around a couple, like 4 stakes under pressure and clamped together and just kind of meh. Whereas really nice high-end race stuff, especially going into like turbos, it'll be very smooth and gradual over a long period of time until it's all just the collector where the tubes meet. Following along so far? That's why I demonstrated this. Because in my header anyways, the tubes just kind of do this. And just come out very quickly, and they don't transition smooth, relatively speaking. And they're just kind of sloppy. It's done really quick, really fast, and it's just a cut. It's literally, these are cut, and then you have something mounted around like so, which works, but I don't recommend it. Again, this is a very rough diagram, so bear with. Usually speaking, as a general rule, depending on your header length, and this is something to keep in mind when choosing headers or any kind of exhaust system, is, are your heads ported, polished, whatever the case may be? How long are the runners? And that's something to keep in mind definitely every time. How large in diameter are they? Because that determines how much they can flow, and will it fit? That's the one that always seems to be forgotten. And as engine masters proved, you can bash them a fair bit before you actually lose any kind of power. But we'll talk about that another day. Now, with regards to length, this is the important one. Long tube headers usually are great for high-end horsepower, high RPM horsepower, because they're moving so much air so fast that it's getting that fluid hammer, again, that we've talked about before, moving, that at those RPM, it is accelerating the air coming out because it's drawing so much vacuum, because it has a long, long time. Usually, these are best suited for high RPM horsepower and kind of lower-ish torque figures, as a general rule. Medium length headers are usually your just all-around good jack-of-all-trades style header. They're not great at high-end horsepower, they're not great at low-end torque, they're somewhere in the middle, as the name suggests. Shorties, like what I got, are excellent at low-end torque. And the reason being is because the exhaust pulses come together so quickly, they're able to scavenge off of each other. That means as one exhaust valve closes, the pulse has still enough energy that when it passes, say, alright, say this is cylinder 1, this is, we're talking inline force just for the sake of discussion, cylinder 1, 2, 3, 4, in that colored order. As cylinder 1 closes, cylinder 2 opens up. Has cylinder 1's positive pulse passes through, it starts drawing vacuum because there's no demand left. Cylinder 2 just opened, and that vacuum then rushes back upstream to the incoming charge leaving cylinder 2, and therefore helps scavenge it. Whereas in longer headers, that pulse has a little more time to dissipate. And because it's dissipated over a longer period of time, it's better suited for high velocity air rather than low velocity air. Follow along? Kind of, sort of. Like I said, long tube headers are great for high-end horsepower. Shorties are great for low-end torque. And medium length headers are somewhere in between. They don't make as much torque, in theory, as shorties, but they make more horsepower than shorties. But they don't make as much horsepower as long tubes, but they make more torque than long tubes. Again, somewhere in between. And exhaust scavenging is kind of a science in and all of itself. We're already an hour deep into the lesson, and I'm trying to explain this as in simplest of terms as physically possible. It's fluid dynamics is something I taught myself, and if you need a practical demonstration, go to a Burger King, get a straw, get a drink, start sucking as hard as you can on that straw, and then immediately slam your tongue over the top of it. You'll feel a little push at the tip of your tongue on the inside of the straw. That is that fluid hammer we were discussing earlier. Follow along, class? Yes? Good. This is practical engineering. It's very simple, very basic. It's not that difficult to understand. Now, as the air moves down, depending on the diameter of your exhaust system also depends on a couple of factors. Usually guys will want like 3-inch exhausts on gas motors, and I've heard guys going as much as a 6-inch exhaust tip on their diesels. Don't ask me why, because it kind of defeats the purpose. Depending on your application, whether it be gas or diesel, if you're looking for low-end torque in terms of power production, you're usually going to want to use something along a 2.5 to 3-inch exhaust. Usually, not always. 3-inch exhaust is more for higher velocity air, so higher RPM engine speeds, therefore allowing for freer flowing air. And depending on your setup, can matter a lot. There are actually, believe it or not, catalytic converters. Yes, I know, a lot of young hot rodders may not be too familiar with what those are. In the early days, just an exhaust restriction. Nowadays, there are catalytic converters that can actually improve horsepower. Go figure. And my thought on that is because of their honeycomb design. We'll go over here and just make a very basic grid. Now this is going to be a demonstration of the cross-section of a catalytic converter as you were looking at it going through as an exhaust pulse. Now bear in mind, what you're looking at here is, we're talking the thickness of a human hair, basically. That's how small we're talking. Like I said, it's a honeycomb looking thing. Now, why does this matter? Well, again, these lines, thickness of a human hair, thereabouts, can actually smooth out an exhaust pulse. What that means is that because a pulse has a hole going down the tube, radiates circular, like so. You have your point of origin, and this just, it's actually dome shape, I should say. So, sort of shaped like that, as it's going down the tube. To give you an idea in 3 dimensions. Because of this, the pulse tends to get uneven. By forcing it through a honeycomb like this, depending on how the honeycomb is set up, can actually smooth it out to be much flatter. So instead of looking like this, it'll look a little something more like that in 3 dimensions. Which you would want if you're trying to get a little bit more kick out of the motor. Now the reason you would want that is because that's a harsher line. So therefore you're drawing a little bit more vacuum and have a little more positive pressure in the pulse. As a result, the honeycomb not only works more effectively to generate horsepower if you have one of those actual horsepower boosting catalytic converters. It also means that if you have, say, a Y pipe, or even an X pipe or an H pipe, which I'll demonstrate now. H pipe, very simple. Motor Trend's already explained this. This is an H pipe. Y pipe for a single exhaust, and an X pipe. Actually, no, we need to scooch you over one more. Which, believe it or not, X pipe, if you're looking for horsepower production, is the way to go, but it's not always feasible because of the body restrictions. Let me just do this so I can differentiate. Following along so far? Yes? Good. The black is where the crossover is, or merge is. Depending on your setup, a Y pipe might help you. Let's say 350 Chevy. 350 Chevy. Very common motor, everyone knows it. Loves it or hates it, depending on who you are. And is basically the standard motor in industry right now for hot rodding, whatever the case may be. Now, love it or hate it, this is the basic setup of H, Y, and X. Y pipe is usually what the less sporty-er models come with regards to V-style engines. H pipes you don't really see OEM manufacturers doing. You might see an X pipe on an OEM car, but an aftermarket exhaust system will always help with power production because it usually be a little bit larger in diameter, and depending on how you're tuning your exhaust, again, we're talking minutia here. We're talking at most 10-15 horsepower gain from an entire exhaust system. At most. So bear that in mind. H pipes are usually done by home gamers in their garage, has a way of kind of cheating the system, I guess you could call it. Sure, that's more appropriate. Some manufacturers have actually gotten pretty clever. For instance, on my van, I have a 97 Dodge van, 2500 high top, long haul van. Why does that matter? Because Chrysler got sneaky with the exhaust system on it. It actually uses the catalytic converter as the merge from left and right, from driver and passenger side bank, which is rather clever actually. It forces both through and it keeps production costs down, which is actually rather smart. It also allows for better relocation, yada yada yada. We're going to discuss that another time. But needless to say, we've gone through the intake, we've gone through header design, now we're talking exhaust systems. Now, H pipe, what ends up happening is as one bank's pulse finishes up, another bank will be wanted to draw from side to side. This is alright and is, depending on your exhaust setup, slightly better than a Y pipe. Again, depends heavily on your headers. Again, we're talking minutia here. We're talking at most 15 to 20 horsepower, and that is if you're making a lot of power to begin with. Now, in terms of power production, an X pipe is the way to go. But because of the complexity involved, an X pipe may not always be feasible because you have to take into account the wheel setup, you have to take into account the body pan, you have to take into account the hanger, the transmission, the drive shaft if you have a rear-wheel drive engine. It's very complicated and it is not always the most feasible thing to do. or you could have a true dual exhaust, like so, with no crossover. Now this works, and you definitely get a different sound. What you're looking at here is sound. Now, if you had done it right, a wide pipe setup for your exhaust might actually be the best setup. I have heard stories of guys that have made a giant pipe organ of a header, single header for their V8 engines, because they had spent the time and calculated out how fast the air is moving, how long it would take to travel down X amount of distance down a given diameter of tube, and they have figured out that by having cylinder 1 through 8 at these different lengths and coming together at different times with different cylinders, they figured that they could maximize the scavenging effect of the negative pressure zone on the backside of a pulse to maximize horsepower, which is great, but that kind of setup is beyond tedious, beyond expensive, and depending on your setup on your vehicle may not be the most cost-effective solution. Now, if you could figure that out, awesome. Because, again, we're talking minutia here. In a setup like that, you might actually see 20 or 30 horsepower, potentially, and maybe just as many pound-foot, which is excellent. But again, we're talking an incredibly complicated system. For example, the dual plane intake that we were talking about before, same principle, except this is easier because it's all located in one single spot. Whereas to do the same kind of setup on your exhaust is nightmarishly difficult, because you have to feed one bank to the other and so on and so forth. I'm actually trying to remember. 1/8 is the firing order of a small block offhand. I can't remember. We'll take a quick break, grab a snack, grab a drink, take a whiz, and we shall come back shortly. Hey Ray, how's it going? Now, before I forget, let's see. Most common engines, anyways, for small block Chrysler and big block Chrysler have a firing order of 184-36572. Now, to do a single header style on that kind of motor would, again, like I said, require a pipe organ of tubing. But for the moment, class is dismissed because I have to go somewhere, and we're already over an hour long in this discussion. We will discuss firing orders and their importance to the engine next time, and I shall see you shortly.